Hello everyone, this is Dr. Webb. In our last video we talked about local maxima and minima, and so now this is a real natural time to talk about an important application of maxima and minima, which is really one of the most important applications and uses of calculus, and that's to do optimization. So just quick overview, what is optimization? So the idea is if you're given a function and you want to find either the maximum or minimum value on some domain that is closed and is finite in whatever the right measure of the region is. And so if we're doing this in one dimension, we'd be talking about length. If we're doing this in two dimensions, you'd want a region with finite area. And if you're doing this in three or more dimensions, then you'd be talking about volumes and hypervolumes. But you want it to be finite space, a bounded space in some sense, right? And so for Calc 1, length we're talking about over some closed interval. But for two or more, this suddenly can get to be a whole lot more interesting in terms of the types of regions that you're talking about. Okay, so from Calc 1, what an optimization problem would look like is you're trying to find the maximum or minimum value of f of x on some closed interval a to b. Right, so how did we go about doing this in Calc 1? So the strategy was first find the critical points of the function inside the interval. Right, so particularly this usually would mean you're trying to find when the derivative of the function equals 0, where the x are between a and b. So that was the first important part. Find those critical points. Okay. Then you would need to make sure that you include the two endpoints as critical points. Those are places where the maximum and mins always can happen. Okay, so you have the critical points you got from inside the interval. You include the two endpoints of the interval. Those are all your critical points, and so then the last step is to check the value of the function at each of those critical points. Whatever the highest value is, that's the maximum of the function. Whatever the minimum is, that's the lowest value. Whatever the lowest value is, the minimum of the function on that interval, right? And so just a game of finding the inner points. Some are inside the interval. You have the 2 points on the outside. The maxes and mins have to take place at one of those critical points. Okay, so what about if we're doing this for two variables? We want to find the maximum or minimum of a two-variable function on some closed region R. So we can think R, this is going to look a whole lot more exotic, say, than just some interval, right? Because you've got an inside, you've got boundaries. The boundary are no longer just 2 points. Now you can have boundary curves, and then you can even have these corners where the curves change from one to another. And so this means that the strategy is going to be a fair bit more involved, but still sort of the basic idea. So the basic strategy is going to be, first, same as before, look on the inside. So if this is our R, we're looking for the inside points where the gradient is equal to 0. Okay. So this is very similar to what we did in Calc 1. Okay. Now the boundary is where it gets more interesting. In Calc 1, the boundary was just 2 points. Now for the boundary, we have, say, a number of different curves. Let me kind of draw roughly what they could be. But on each of these curves, by being a curve, these are each one-dimensional. And since they are inherently one-dimensional, that means Calc 1 calculus can solve the optimization problems on them, right? And so we're just going to use Calc 1 techniques to look for. So you find some, say, parameterization of the curve, or you have it written as y equals x squared. You plug in x squared wherever you see y. You're able to get these down in some way to one variable, and then you're just doing one variable optimization. So when we say use Calc 1 techniques, this is get the function down to one variable on each curve. And again, you can use a vector function parameterization of that to get it all down to t. If you have it as y is equal to some nice function of x, you just plug that function in wherever you see y and get everything down to x. Whatever you need to do. Now, look, so for this region it has three parts, the blue part, the green part, and the red part. That means that really for each of those parts you're doing a Calc 1 optimization problem, right? So depending on how bizarre, complicated your boundary is, this is the part that can really take a fair amount of time to do. And then lastly, don't forget the corners. The corners, by the corners I mean where the boundary curves change from one to another, right? So you need to make sure that these are all included as critical points. And so now you've got critical points from the interior, from the boundary curve, including the corners. These are all the places that critical points can occur. So once you have all of these critical points, plug each of them into the function, and then check the value of the function in each of them. Whichever one gives you the biggest value, that's the maximum. Whichever one gives you the smallest value, that's the minimum. So I went kind of through a fairly fast rundown of the strategy, but these problems generally take a fair amount of time to do. And so I think I'm going to use the rest of this video just to go through this one, to be honest, fairly simple example of how to find maximum and minimum values of a surface over a region, right? So our function here is x squared minus 2xy plus 4y. And we're doing this over the closed region that's bounded by the parabola y equals 9 minus x squared. So that is if we're drawing this on the xy plane, 9 minus x squared, it's going to hit the x-axis at 3 and negative 3, and then our other bound is the x-axis. So we're looking at it on this region right here. Right. And so if we're looking at this, how are we going to go about and do this following the strategy? Well, first, we're going to be looking at what happens on the interior. Right. Secondly, for the boundaries, we really have two boundary curves here. We have the parabola is one boundary curve, and then we have the x-axis is the other boundary curve. That's what we're going to be doing second. And then lastly, we don't want to forget our two corner points right here are at 3, 0 and minus 3, 0. Okay, so let's get going with the interior. So for the interior, this is where we're looking for the gradient equaling the 0 vector. So let's get the gradient. So f of x here is 2x minus 2y. F of y is going to be minus 2x plus 4. So we're going to set each of these equal to 0, and probably fy is probably the best one to deal with first. So if I have minus 2x plus 4 equals 0, I'm going to have 4 is equal to 2x. So x has to equal 2. And then plugging that back into the other one. So if we have plugging 2 in for x, we're going to have 4 minus 2y. Set that equal to 0. 4 is equal to 2y. So y is equal to 2. So we have one critical point. Should double check that this is on the interior of this. So if x is 2, y 2, sure looks like it is, but to double check, if I do 9 minus 2 squared, I get 4. So 9 minus 4 is equal to 5. And so my function value there is up there. And my y value of my point is 2. So it's definitely inside of there. Okay, so we have one critical value, 2, 2. Next, let's think about the two boundary functions. Okay, so first let's do the parabola. Let's get ourselves a place. Okay, so we're looking along the parabola. Y is equal to 9 minus x squared. So we've got y nicely written as a function of x. So that means that we can just plug this into the function x comma 9 minus x squared. And so what's that going to give us? X squared minus 2x times 9 minus x squared plus 4 times 9 minus x squared. And so if you look now, this is all in terms of x. There are no y's there anymore, and so now this is just an optimization problem with x. Okay, so our function now, we've got x squared minus 2x times 9 is 18x plus 2x squared plus 4 times 9 is 36 minus 4x squared. This should be 2x cubed. And so we can organize this as being 2x cubed. X squared minus 4x squared is going to give me minus 3x squared minus 18x plus 36. So this is the function we're trying to optimize. So how did we do that in Calc 1? Take the derivative. So f prime here is 6x squared minus 6x minus 18. Set that equal to 0. I can divide by 6's everywhere. I get x squared minus x minus 3 equals 0. Don't think that has any nice roots, so we're going to use the quadratic formula. X is going to be, b is minus 1, so I have 1 plus or minus 1 squared minus 3 times 4 times 1. So that minus minus is going to give me plus 12 all over 2. And so this is 1 plus or minus square root of 13 divided by 2. And just make things a little bit easier, let's convert this into a fraction. And so our x values can be, if I take plus, it's going to be 2.302 about. And when I take the minus, I get minus 1.302. If you notice that these are both between 3 and negative 3, and that was sort of the bounds of our x values. That's where they cross the x-axis. And so these are both inside of there. We need to get the y values out of this. And so we're going to get the y values just by plugging these back into here. And so y for this one is going to be 9 minus 2.302 squared, which is about 3.701. And using the minus 1.302, so this would be 9 minus 1.302 squared, and that gives us 7.305. Okay, so the 2 points that we get from this boundary are 2.302, 3.701, and minus 1.302, 7.305. Okay, and so don't forget that we had 2 comma 2 from before. Okay, so that covers the parabola. Next, we have to look at the x-axis. Okay, so let's give ourselves some blank space to do this. And so now we're focused on this on the x-axis. And so on the x-axis, we're looking at, the x-axis is, the points are going to look like x, and the y values are going to be 0. And we're looking at our x values going from -3 to 3. So if I plug in x comma 0 in here, all the y's are turning to 0. I'm going to be left with x squared minus 0. 2x times 0, it gives me 0. Plus 4 times 0 is 0. And so it's just x squared. Again, this is only in terms of x now, so we're doing optimization just on x squared. Take the derivative, I get 2x. Set that equal to 0. I get x equals 0, being our one critical point coming from this part of the boundary. And so that's going to contribute the point 0, 0. Okay, and so now putting this all together, so just recall the picture. Our region R looks like this. Okay, and so first critical point we got from the inside was 2, 2. And so that's sitting about right there. The next critical points we got were coming from the what was happening on the parabola, and one was, let's say it's approximately right there. This is not totally to scale, and so this is at 2.302, 3.701, and then there was another one that was more like up here, minus 1.302 and 7.305. And then lastly, we got, for the x-axis, we got a critical point at the origin. And we don't want to forget the 2 corner critical points. Okay, so in total, you can see we need to check 1, 2, 3, 4, 5, 6 points out of this relatively simple function. And so last but not least, we're going to plug these each into our f. And so if you go back and plug 2, 2 into the function, that's going to spit out 4. If you plug in 2.302, 3.701, that's going to give you 3.064. If you do the other point on the parabola, minus 1.302, 7.305, because of that minus sign, this actually makes this pretty big. This is 49.937. The minus sign there and the 7 in the y coordinate work together to make this big. If you plug in the origin into this, you get out 0. If you plug in 3, 0, you get 9. And minus 3, 0, you also get 9. And so looking at these, our winner for the biggest value is right there. And so this point right here is giving the max, and the minimum is coming from the origin. It looks like this is non-zero everywhere. This is positive everywhere except for the origin on this region. And so That is our minimum. Okay. So this is the idea. Again, if your boundary region has, this boundary had two pieces, so we had to do two Calc 1 optimizations on the boundary. If the boundary is a square, that might seem simpler, because squares seem simple, but those have four sides, and so four sides would mean you have to do four optimization problems, one for each of them. So this is just the way that optimization goes. As you go up in variables, sometimes what that means is you just have to do, it's like you do more Calc 1 problems to figure it out. So that is all I have for this video. I will see you again soon.